We're going to start the trigonometry course by talking about right-angled triangles, which is a good place to start. So these are, simpler to deal with than general triangles. A right-angled triangle is just a triangle that has a 90-degree angle in one corner of it. The way to describe these triangles is by functions known as sine and cosine. Sine and cosine are a way of talking about the ratios of sides of a different triangle. So really, if you know the sine of one of the angles, or the cosine of one of the angles in a triangle, it's pretty much a good description of what that right-angled triangle is. Okay, so think of sines and cosines of the triangles as labels, if you will. What actually is a sine or a cosine? What am I talking about? If we label the sides of a triangle as opposite, adjacent, and hypotenuse with respect to an angle that we're talking about, the sine of this angle is defined as the ratio of the opposite to the hypotenuse. Okay. Similarly, the cosine of the angle, which is some other function, is defined as the ratio of the adjacent to the hypotenuse. And these are really hard for people to get their heads around, right? As I've mostly noticed. What does this really mean? Well, this is a function, just like y equals x squared. X squared is a function, right? It's a squaring function. Adding 2 is a function. Sine is just some function, okay? Let's investigate that a little bit. So, this makes sense. Sine makes sense if theta, or angle, is between 0 and 90 degrees by the definition that I've given you, right? You can't really extrapolate that so far outside of this range, because angles in a triangle have to add up to 180. You can't really get a right angled triangle where the angle is bigger than 90 degrees. And we don't really know what we mean by negative angle yet in this context. So whenever theta is between these, it looks like sine will take some value. It'll take the value of this side divided by this side. So currently for this triangle, because this side is shorter than that side, the actual value of this will be, looks like a fraction, maybe about a half, possibly, by what we're seeing here. So it's not exactly clear what it could be, but let's sort of investigate that a little bit. I'll give you some exact values of sine so that we can begin to discuss and explore these functions. So if I draw this triangle in blue, pretty similar to the one we had upstairs, and I'm going to say that this angle here is 30 degrees. So you might want to just draw that in the paper in front of you if you want to follow along. So what is sine of 30 degrees? If you use a protractor and measure it out, you'll find that the ratio of the opposite to the hypotenuse, they're exactly 2 to 1. In other words, if we make this 1 centimeter, you'll find that this has to be 2 centimeters just by the way the triangle is constructed. So we conclude that sine of 30 is a half. Okay, and let's have another example. Suppose we have an isosceles triangle. Okay, and similarly, well, first of all, if it's isosceles right-angled, what can we say about the angles? They're the same, right? I mean, they don't look the same in this picture, but that's what I meant to do. Now, if they're the same and they add to 180, then each of these must be 45. Hope you agree. We can intuitively work out then what the sine of 45 is. So all we've got to do is give one of these sides a length of 1, and then this is 1. Now, using Pythagoras Theorem, which we hopefully all know, if we say this side is x, then what is x? Using Pythagoras Theorem, find x. So x squared is equal to 1 squared plus 1 squared. So I'm going to get 2 on this side. I can square root both sides, and I get x must be the square root of 2. So this side, if the other two sides are 1, the hypotenuse must be the square root of 2. Which means, what is sine of 45? Well, we can just, again, see that it's the opposite over the hypotenuse, and it must be 1 divided by root 2. Sine of 45 is over h, so this is 1 divided by root 2. Okay. I can also rationalize this third if I wish to, by multiplying top and bottom by root 2. Of course, this is just multiplying by 1, so it doesn't change the actual number. And I get a much more intuitive root 2 divided by 2. Okay. So that's what we've got so far.